What if every choice you didn't make actually happened in another universe? According to modern physics, this isn't science fiction. It's a serious theory called the quantum multiverse, based on the many worlds interpretation of quantum mechanics. In this view, the universe doesn't choose a single outcome when something is measured. Instead, reality splits, creating multiple parallel universes where every possible outcome exists. No collapse, no randomness, just one evolving quantum wave, branching endlessly into countless worlds. This idea doesn't come from imagination. It comes directly from the equations that describe our universe. So the real question is, are we living in just one universe or one branch of many? What if our universe isn't the only one? Not in a sci-fi way, not in a spiritual way, but based on real theoretical physics. Here's what scientists actually mean when they talk about the multiverse. Let's start with quantum physics. At the smallest level of reality, particles don't behave like solid objects. They exist in multiple states at once, until they're measured. One interpretation of this is called the many worlds interpretation, proposed by physicist Hugh Everett III. Instead of a single outcome being chosen, every possible outcome happens, each in its own universe. So every time a quantum event occurs, reality splits. In one universe, one thing happens. In another, a different thing happens. You don't notice the split because you split too. Each version of you only experiences one outcome. Now let's zoom out, way out, to cosmology. Right after the Big Bang, the universe expanded incredibly fast in a process called inflation. Some versions of inflation theory suggest this expansion never fully stops. Instead, it stops in patches, forming individual universes, like bubbles in an endless cosmic foam. Each bubble universe can have different physical laws, different constants, different particles. Our universe may just be one bubble among countless others. There's another idea that comes from string theory. String theory suggests that there are enormously many possible ways a universe can exist, on the order of 10 to the power of 500. Each possibility corresponds to a universe with its own rules. This could explain why our universe seems so perfectly tuned for stars, chemistry, and life. Not because it was designed, but because we're living in one of the few universes where observers can exist. And then there's the most extreme idea of all, the mathematical multiverse proposed by cosmologist Max Tegmark. This idea says that every mathematically consistent structure exists physically. If something can exist without contradiction, then it does exist. Our universe is just one mathematical structure among infinitely many. Now, here's what physics doesn't say. There's no evidence that universes can interact, we can travel between them, or that we can feel our other selves. These ideas are theoretical, not proven, but they're not made up. They come from following well-tested equations, even when the conclusions feel uncomfortable. So the multiverse isn't science fiction. It's not philosophy pretending to be science. It's what happens when physicists take their best theories seriously and refuse to stop where things start to feel strange. Whether the multiverse is real or not is still unknown. But one thing is clear: reality may be far bigger and far stranger than a single universe. They're not imagining parallel worlds stacked next to ours. They're talking about a branching structure of reality, where separation happens faster than thought itself. You don't see the branches for the same reason you don't see individual atoms. They're not gone, they're just inaccessible. Why we don't see the multiverse if all these universes exist? Why don't we ever see them? Why doesn't reality look split? The answer is something physicists call decoherence. In quantum physics, particles can exist in many states at once, but they're incredibly fragile. The moment a quantum system interacts with its environment, light, air, heat, particles, those possibilities stop overlapping. They separate, not by collapsing, but by losing the ability to interfere with each other. That separation is decoherence. Think of it like this. At first, reality is like multiple transparent images stacked together. Once decoherence happens, those images drift apart so completely that they can never overlap again. Each branch becomes its own self-contained universe. From the inside, it looks like one thing happened. From the outside, if that even makes sense, everything happened. This is why the multiverse doesn't feel chaotic. Each universe follows consistent laws, clear cause and effect. A stable timeline. Decoherence hides the quantum weirdness before it ever reaches our everyday scale. This also explains why we never experience being in two realities at once. Your brain, your body, your atoms are constantly interacting with the environment. You decohere almost instantly, so you only ever experience one branch, even if others exist. This idea builds directly on standard quantum mechanics. It doesn't add new forces, it doesn't break physics, it just takes the math literally. That's why many physicists prefer this explanation over mysterious wave function collapse. No magic moment, no special observer, just physics doing what physics already does. And here's the part that really shifts perspective. If decoherence is real and experiments strongly support it, then reality doesn't choose a single outcome. It allows all outcomes, then isolates them from each other, which means the universe isn't economical. It's extravagant. So when physicists talk about the multiverse, they're not imagining parallel worlds stacked next to ours. They're talking about a branching structure of reality, where separation happens faster than thought itself. You don't see the branches for the same reason you don't see individual atoms. They're not gone, they're just inaccessible. Does the multiverse destroy free will? If every possible outcome happens, does that mean your choices don't matter? This is one of the biggest objections physicists and philosophers raise about the multiverse. And the answer is subtle. First, let's clear something up. Physics already tells us that the universe follows laws. Even without the multiverse, particles obey equations. So the question of free will didn't start with many worlds. The multiverse just forces us to be honest about it. In the multiverse picture, when you make a decision, reality branches. In one branch, you choose option A. In another, you choose option B. But here's the key point. You never experience the branching. You experience making a choice. From your point of view, you deliberate, you feel uncertainty, you decide, you live with the consequences. Nothing about that experience disappears. So does free will vanish? Not really. It changes meaning. Instead of "I could have chosen differently" in the same universe it becomes, there are versions of me that chose differently. But this version is defined by the choice I experienced. Your identity is branch relative. And that's enough for responsibility, meaning, and intention to exist. Now here's something even more important. The multiverse does not say that everything happens in a random way. The branching follows probabilities. Some outcomes are extremely unlikely. Others are overwhelmingly likely. You don't suddenly branch into absurd realities every second. The structure is tight, predictable, lawful. And this leads to a surprising conclusion. In a single universe model, one outcome happens, all others are erased. In the multiverse, nothing is erased. Reality doesn't throw information away. It keeps it separated. That actually makes the universe more complete, not less meaningful. So your choices don't become pointless. They become defining. Each version of you carries forward the consequences of the choice they experienced. No version gets to escape that. The multiverse doesn't say nothing matters. It says everything that can happen matters somewhere. And what matters to you is the branch you're in. Why time only moves forward. One of the strangest things about reality isn't space, or particles, or even the multiverse. It's time. Because the laws of physics don't actually care which direction time flows. At the fundamental level, most physical equations work just as well backward as forward. If you filmed two particles colliding and played the video in reverse, the equations would still make sense. And yet, you never see. Broken glass reassemble, smoke flow back into a cigarette, heat move from cold to hot. Time only goes one way. Why? The answer lies in something called entropy. Entropy is a measure of how many possible microscopic arrangements a system can have. Low entropy means order few possible arrangements. High entropy means disorder many possible arrangements. And here's the rule that shapes everything. In an isolated system, entropy almost always increases. This is the second law of thermodynamics. Think about a glass falling off a table. When it's intact, its atoms are arranged in a very specific, orderly way. When it shatters, there are astronomically more ways for the pieces to be scattered than to be perfectly reassembled. So entropy increases, not because it must, but because it's overwhelmingly more likely. This is why time has a direction, not because the laws of physics demand it, but because probability does. The arrow of time is an arrow of increasing entropy. Now, here's where things get really interesting. For entropy to increase, it must have started low, very low. And that's exactly what we see when we look back toward the beginning of the universe. The early universe was extremely hot, extremely dense, extremely smooth, which sounds chaotic, but was actually low entropy. Matter and energy were spread out in a highly uniform way, leaving enormous room for entropy to grow. This low entropy beginning is what makes time's arrow possible at all. But here's the mystery. Why did the universe start in such a special low entropy state? Physics doesn't yet have a final answer, and this is where the multiverse enters the story again. In some multiverse models, there isn't just one beginning. There are countless regions of space-time, each with different initial conditions. Most of them are chaotic, high entropy, unstructured. But once in a while, purely by chance, a region starts in a low entropy state. And only in those regions can time have a direction. Structures form stars, ignite life, exist observers, ask questions. We find ourselves in such a universe, not because it's typical, but because it's necessary for us to exist at all. From this perspective, the arrow of time isn't a universal rule. It's a local feature of our cosmic neighborhood. In other regions of a larger multiverse, time might flow differently, or not have a meaningful direction at all. Now connect this back to the multiverse and branching realities. Each time a universe branches, entropy increases. Information spreads into the environment. Possibilities separate. Coherence is lost. This means branching and the arrow of time are deeply connected. The future feels open because entropy hasn't increased yet. The past feels fixed because entropy has already done its work. This is why you remember the past but not the future, why causes come before effects, why choices feel real, why experience has a direction. So time doesn't flow because the universe tells it to. Time flows because the universe started in a rare, ordered state and has been unwinding ever since, like a wound spring, slowly releasing its tension. And that leads to one final, unsettling thought. If the arrow of time depends on entropy, and entropy depends on initial conditions, then time itself may not be fundamental. It may be emergent, a byproduct of probability, structure, and perspective. Why the universe can be experienced at all so far, we've talked about. Multiple universes, branching realities, time flowing forward, entropy increasing. But there's one thing we've quietly been assuming this whole time. That the universe can be experienced. That something inside it can observe, remember, and ask questions. Why is that even possible? Physics doesn't start with consciousness. It starts with particles, fields, equations. And yet, somehow, out of all that structure, comes experience. Not just reactions, but awareness. Here's the key point physicists agree on. Consciousness is not something added to the universe. It's something that emerges from it. Your brain is made of atoms. Those atoms follow physical laws. Neurons fire, signals propagate, information is processed. Nothing supernatural is required. But when information is processed in the right way, something remarkable happens. The system becomes aware of itself. From a physics perspective, consciousness is best understood as a process that integrates information across time. It remembers the past. It predicts the future. It builds a model of the world and places itself inside that model. Now here's where this connects directly to time and the multiverse. You only ever experience one moment at a time, but that moment feels continuous because your brain links together many instants into a flowing narrative. That narrative depends on memory, low entropy past, anticipation, open future, causality, the arrow of time. Without the arrow of time, consciousness, as we know it, couldn't exist. This means awareness is time directional. You are not just in the universe. You are riding the universe's entropy gradient. Now consider the multiverse again. In a branching universe, many futures exist, but you only experience one because experience itself decoheres. Each conscious observer is locked into a single branch, not by force, but by physics. This leads to a fascinating consequence. The universe doesn't need observers to exist, but observers need very specific universes to exist. Universes with stable laws, long-lasting structures, increasing entropy time, with a clear direction. Those universes are rare. But in a multiverse, rare things happen somewhere. This idea was explored deeply by physicists like Ludwig Boltzmann, who realized something unsettling. If the universe is large enough and old enough, random fluctuations can briefly create observers. These hypothetical observers are called Boltzmann brains, not because they're likely, but because they reveal something important. They show us that not all observers are equal. Most random observers would experience chaos, but we experience order, consistency, deep structure, which tells us something profound. We are not random fluctuations. We are products of a long, stable, low-entropy history, and that history matters. So consciousness isn't floating above physics. It's anchored in entropy time structure law. It's what happens when the universe becomes complex enough to model itself. And here's the quiet conclusion of this chapter. The universe doesn't just exist. In rare places, it knows that it exists. Not because it was meant to, but because, given enough space, time, and possibility, eventually matter learns to ask questions. Did the universe have a beginning? When people hear Big Bang, they imagine an explosion in space. But the Big Bang wasn't an explosion in space. It was the expansion of space itself. Every point moved away from every other point. There was no center, no edge. And when we trace that expansion backward, we reach a moment where density, temperature, and curvature become extreme. Physics breaks down, not because nothing existed before, but because our equations stop working. So the honest answer is, we don't know if the universe had a true beginning. We only know how far our theories can see. What could before the Big Bang mean? When people ask what happened before the Big Bang, they're asking a question that feels natural, but may not be well defined. Because in modern physics, time is not a background stage. Time is part of the universe itself. It bends, it stretches, it can even slow down or speed up. And according to our best models, time itself began behaving the way we know it at the Big Bang. So, asking before the Big Bang might be like asking what's north of the North Pole. There may not be an answer, not because it's hidden, but because the question assumes a structure that didn't exist yet. But physicists don't stop there. They ask whether time could have existed in a different form. Some theories suggest the Big Bang wasn't the beginning, but a transition, a phase change. like ice melting into water. In these models, the universe existed in another state, perhaps contracting, perhaps quantum and timeless, perhaps governed by rules we don't yet understand. The Big Bang would then be a boundary, not an origin. Other ideas imagine a cosmic bounce, a universe that collapsed under gravity, reached a dense quantum state, and rebounded into expansion. In this view, our universe has a past, but not one we can directly observe. Information may not survive the bounce cleanly. Memory could be erased. Time might reset. There are also models where time exists locally, but not globally. Different regions of reality may have their own arrows of time, their own beginnings, their own histories. In such a picture, asking for the beginning of everything may be the wrong question entirely. What physics tells us, honestly, is not that there was nothing before the Big Bang. It tells us that our current theories cannot describe that regime. And instead of inventing answers, good. Physics stops at the edge and admits uncertainty. That uncertainty is not weakness, it's discipline, eternal inflation, and endless creation. One of the strangest consequences of modern cosmology is that the universe may never stop being born. In inflation theory, space expands rapidly due to a high-energy vacuum state. In some versions, that vacuum is unstable, but only locally. It decays in patches. Each decay creates a universe. While one region stops inflating and forms galaxies, space around it continues to expand faster than light can travel. That means new regions are constantly forming, forever out of reach of each other. This process is called eternal inflation. It has no end, and possibly no beginning. In this picture, the multiverse is not a collection of universes sitting side by side. It's a process, a cosmic engine that never shuts off. Universes don't appear in space. They appear as space. Our universe would be just one bubble in an endless sea of expansion. Not special, not central, not privileged. Just one place where inflation stopped long enough for structure to form. This idea feels excessive, wasteful. Why so much reality for so little life? But physics doesn't optimize for efficiency. It follows equations. And if those equations allow endless creation, then endless creation happens. Why the universe is simple at its core, at first glance, reality looks complicated. Galaxies, cells, brains, civilizations. But when physicists strip things down, they find something surprising. Simplicity, a handful of particles, a small number of forces, compact mathematical laws. The same equations govern everything from the inside of an atom to the motion of galaxies. This simplicity is not fragile, it's powerful, because simple laws can generate endless complexity when applied repeatedly over time. Like a few musical notes creating infinite melodies. If the laws were more complicated, small errors would accumulate. Structures would collapse. The universe would be noisy, unstable, and short-lived. Instead, the universe is lawful enough to last, long enough for stars to burn slowly, for chemistry to unfold, for life to experiment. Complexity is not built into the laws, it emerges from them. Fine-tuning without design, some numbers in physics seem unnervingly precise. Change gravity slightly, and stars collapse or never form. Change electromagnetism, and atoms fall apart. This is called fine-tuning. For a long time, this puzzled physicists. Why these values? Why not others? The multiverse offers an unsettling answer. There may be no reason. If many universes exist with different constants, then most are sterile. A few are structured, and observers will always find themselves in one of the rare survivable ones. This isn't purpose, it's selection, like a puddle fitting the shape of the hole it's in. The universe doesn't need to be tuned for life. Life tunes itself to the universe it finds. Why the universe is not friendly? The universe is vast, cold, mostly empty. radiation-filled, lethal to life almost everywhere. This tells us something important. We are not the goal of the cosmos. We are a side effect. Life survives in narrow windows where conditions accidentally align. That doesn't make life meaningless, it makes it rare. Meaning is not guaranteed by the universe. It's created locally, by minds. Why space has 3 dimensions. Physics allows many dimensions, but only 3 large spatial dimensions allow stable complexity. In 2 dimensions, orbits are unstable. In 4 or more, forces weaken too fast. Atoms don't hold together. 3 dimensions are not chosen. They are selected. Only here can complexity persist long enough to notice itself. Is reality digital or continuous? At very small scales, space and time may not be smooth. They may be granular, pixelated. There could be a smallest unit of length, a smallest tick of time, beyond which distance stops meaning anything. Or reality may be continuous, beyond our reach. We don't know yet. But either way, what we perceive is an approximation. Why the laws of physics don't change. The universe behaves consistently. Yesterday works like today. Here works like far away. This is due to symmetry. Symmetry enforces conservation, energy, momentum, charge. They don't vanish. Without symmetry, reality would be chaotic, unpredictable, short-lived. Information is deeper than matter. Modern physics increasingly treats reality as information, not stuff, relations, patterns. Even black holes don't destroy information, they encode it, scramble it, hide it. This suggests space and time themselves may emerge from information. Why nothing is ever truly lost. Burn a book. Shatter a star, drop matter into a black hole. The form disappears, but the information doesn't. The universe keeps records, even if we can't read them. The long fade toward the end, stars burn fuel. Galaxies drift apart, entropy increases. Eventually, gradients vanish. Nothing happens. Not because nothing exists, but because nothing changes. When time stops meaning anything, time requires change. Without change, there is no before or after. The end of time may not be dramatic, just quiet. Why there is something instead of nothing. Physics doesn't explain why existence is allowed, but the multiverse reframes the mystery. Nothingness requires explanation. Existence happens wherever it can. Why reality feels strange. Our intuition evolved to survive, not to understand reality. The universe feels strange because we are small. The quiet ending. The universe doesn't promise meaning, but it allows it. In rare regions of space-time, matter becomes aware and asks why it exists. That may be enough. The limits of what we can ever know. As powerful as physics is, it comes with boundaries. Not boundaries of imagination, but boundaries built into reality itself. There are things the universe may never allow us to observe, no matter how advanced we become. The most obvious limit is the cosmic horizon. Light travels at a finite speed. That means we can only see regions of the universe whose light has had time to reach us. Beyond that horizon, there may be galaxies, structures, even entire universes, but they are permanently cut off, not hidden, not destroyed, just unreachable. And the universe is expanding, not slowly, but fast enough that distant regions are receding from us faster than light can cross the gap. Those regions are not just far away, they are forever inaccessible. No future technology can change that. This already tells us something important. Reality is larger than what can ever be known, not in principle, not temporarily, but fundamentally. There are also limits at the smallest scales. If space-time is quantized, there may be a minimum distance below which the concept of location breaks down. Questions like, what is inside this point, may simply stop making sense. Not unanswered, ill-defined. Quantum mechanics adds another boundary. You cannot measure everything at once. The more precisely you know one quantity, the less precisely you can know another. This isn't a flaw in our instruments, it's built into nature. Then there are limits created by complexity. Even if the laws are simple, their consequences can be impossible to calculate in practice. Some systems are chaotic. Tiny differences grow exponentially. Prediction becomes meaningless not because we lack equations, but because reality amplifies uncertainty. And finally, there is the most unsettling limit of all. Some theories may be true without ever being testable. Multiverse models, cosmic beginnings, the ultimate nature of space-time. They may leave indirect fingerprints, but never decisive proof. Physics may point toward them without being able to confirm them. This forces a shift in how we think about knowledge. Not everything real is measurable. Not everything true is provable. Science doesn't promise certainty. It promises honesty. And honesty sometimes means saying, we don't know, and may never know. That's not failure. That's intellectual humility. What matters is not that we reach final answers. What matters is that we map the boundary between what can be known and what must remain open. That boundary is not empty. It's where the deepest questions live. The universe doesn't owe us understanding, and yet remarkably, it allows understanding at all. In small pockets of space-time, matter organizes itself to ask questions about everything else. We are not outside the universe looking in. We are the universe trying to understand itself from the inside, with limited tools, limited time, and limited perspective. And maybe that's the final lesson. Not that knowledge is infinite, but that curiosity survives even when certainty ends. The edge of understanding is not a wall, it's a horizon. And like all horizons, it recedes as we move forward, never disappearing, but always inviting us to continue. Is reality fundamentally random or deeply determined? At the deepest level we can currently probe, reality appears uncertain, not just complicated, but genuinely unpredictable. In quantum mechanics, events don't happen with certainty, they happen with probabilities. You can calculate the odds perfectly and still not predict the outcome of a single event. This is not ignorance, it's built into the theory. A radioactive atom doesn't decay because something nudges it. It decays without a cause we can point to, only a probability. And when the decay happens, no experiment can tell you why that moment and not another. This unsettled physicists deeply. For centuries, physics was deterministic. If you knew the present exactly, you could calculate the future exactly. Quantum mechanics broke that idea, not gradually, completely. Some physicists accept this randomness as fundamental. Reality, at its core, may not be scripted. It may only be statistically constrained. The universe doesn't choose a single path. It samples from many. Others are uncomfortable with that. They suspect the randomness hides something deeper, unknown variables, hidden structure, a deeper level of law we haven't discovered yet. But decades of experiments have placed strict limits on how much hidden order can exist. If there is something underneath, it is profoundly unlike classical intuition. The multiverse offers one way to reconcile this tension. What looks random from inside a single universe may be deterministic across many. All outcomes occur, we just experience one. Probability becomes a measure of how often a particular outcome appears across branches. In that picture, nothing is truly random, but nothing is uniquely chosen either. Reality unfolds in all allowed ways, and experience selects a single thread. Yet even this doesn't fully restore certainty, because from the inside, the future still feels open, decisions still matter, outcomes still surprise us. So physics leaves us with a quiet conclusion. Reality may be neither fully random, nor fully determined in the way we once imagined. It may be structured possibility, law without certainty, order without prediction. And that may be the deepest kind of stability the universe allows. Meaning, in a universe that doesn't care, physics is indifferent. It does not reward effort. It does not punish failure. It does not care whether life exists or not. Stars burn. Galaxies collide. Entropy increases. The universe follows its rules without preference or intention. For some, this feels cold. If the universe doesn't care, where does meaning come from? But physics never promised meaning. It only describes what happens. Meaning is not something written into the equations. It's something that emerges locally, in systems complex enough to remember, to care, to choose. Life creates meaning the way stars create light, not because it must, but because conditions allow it. In a universe with no built-in purpose, meaning becomes fragile, but it also becomes real, not imposed from outside, not guaranteed, chosen. The multiverse doesn't erase meaning. It makes it contextual. Your experiences matter because you experience them. Your relationships matter because they shape a conscious history that exists nowhere else. Even if countless universes exist, this moment only happens here. This branch, this configuration, this awareness. Nothing else can replace that. Physics tells us we are temporary, local, finite. But it also tells us something remarkable, that the universe allows islands of care inside oceans of indifference. That matter can organize to feel joy, fear, curiosity, love. Meaning doesn't need cosmic endorsement. It doesn't need permanence. It only needs experience. And perhaps that is the final quiet truth physics leaves us with. The universe doesn't care that we exist, but we care. And in a reality governed only by laws and chance, that may be the most extraordinary thing of all. Why the universe is understandable at all, there is a quiet mystery hidden beneath everything physics has revealed. Not why the universe exists, not how it began, but why it is understandable at all. The universe does not have to make sense. It could have been governed by rules so complex that no pattern could ever be extracted. It could have changed its laws randomly over time, or behaved differently in different places with no consistency at all. In such a universe, knowledge would be impossible, prediction would fail, understanding would never take root. And yet, this is not the universe we find ourselves in. Instead, reality is governed by laws that can be written down with a small number of symbols. Equations that fit on a page describe galaxies, atoms, light, and time. The same patterns repeat across enormous differences in scale. This is not obvious. There is no requirement that the universe be mathematically elegant. And yet, elegance keeps appearing, again and again. One explanation is selection. Only in universes with stable, consistent laws can complex structures persist long enough for observers to evolve. If the rules changed too quickly, nothing could remember the past. If they were too chaotic, nothing could learn. Understanding requires regularity. But this explanation still leaves something unresolved. Why mathematics? Why abstract symbols created by the human mind map so precisely onto the structure of reality? Why does an equation written on Earth describe the behavior of stars billions of light years away? Physics doesn't have a final answer, but it offers a clue. Mathematics is not imposed on the universe, it is discovered within it. We don't invent the patterns, we recognize them. Our brains evolved to detect structure, edges, regularities, cause and effect. Those abilities were refined by survival, but they turn out to be powerful enough to glimpse the deep architecture of reality. This doesn't mean we understand everything. Far from it. But it does mean something remarkable. The universe is not opaque. It is not sealed. It allows partial understanding from the inside. That may be one of its most extraordinary features. Not that it exists, but that it can be known. The fragility of understanding is powerful, but it is also fragile. Every theory we have rests on assumptions, approximations, and limits. Physics progresses not by accumulating truth forever, but by replacing models with better ones. Newton's laws were once considered final. They explained motion, gravity, and planets with stunning accuracy. Then relativity showed they were incomplete. Still useful, still accurate in many cases, but not fundamental. Quantum mechanics did the same. It shattered classical certainty and replaced it with probability. Then quantum field theory went deeper. And now, even that may be provisional. This doesn't mean physics is unreliable. It means it is self-correcting. Understanding advances by admitting where it fails. But fragility also comes from elsewhere. Human understanding is limited by finite lifetimes, finite attention, finite computation. There are truths we may never hold in our heads all at once. Some explanations may require levels of abstraction beyond intuition entirely. Already, much of modern physics cannot be visualized. It must be trusted, tested, and inferred rather than imagined. Reality is not obligated to match the shapes our minds evolved to recognize. And yet, despite all of this, knowledge persists. It is passed forward, refined, translated, encoded into language, mathematics, and machines. Understanding does not belong to individuals. It belongs to civilizations. And even civilizations are temporary. This raises a sobering thought. Understanding is not guaranteed to last. It can be lost, forgotten, reset by catastrophe or silence. The universe does not preserve insight. It only preserves information, which means understanding is a local achievement. A brief alignment of curiosity, stability, and memory in a vast indifferent cosmos. But that doesn't diminish it. It elevates it. Because fragile things that persist against entropy are the most remarkable of all. Is reality fundamentally computational? As physics digs deeper, matter begins to look less like stuff and more like process. Particles are no longer tiny objects. They are excitations of fields, patterns of activity, events. At the deepest levels we can probe, what exists is not things, but transformations. This has led some physicists to ask a radical question. What if the universe behaves like a computation? Not a computer inside the universe, but the universe itself as a kind of information processing system. In this view, the laws of physics are not instructions written on matter. They are the rules by which information updates itself. State follows state. Input becomes output. Present becomes future. Space and time, then, are not fundamental. They are bookkeeping tools, ways of tracking how information is related and how it changes. Distance measures how strongly things interact. Time measures how quickly states update. This idea is not science fiction. It appears naturally in several areas of modern physics. Black hole theory treats entropy as information. Quantum mechanics describes reality as evolving probabilities. The holographic principle suggests that the information inside a region is encoded on its boundary. In such a universe, nothing moves in the classical sense. The universe updates, like frames in a movie, except the movie generates itself. This perspective doesn't mean reality is fake. A simulation, if real, is still real to those inside it. What matters is not whether the universe computes, but that structure persists through transformation. And here's the quiet implication. If reality is computational, then complexity is not accidental. It is expected. Given enough time and space, simple update rules generate intricate patterns, galaxies, life, thought. You are not separate from this process. Your brain is a physical system processing information according to physical law. Thought is not outside physics. It is one of its expressions. The universe doesn't need intention to generate intelligence. It only needs rules that allow information to build on itself. Whether or not the universe is literally a computation may never be answered definitively. But the idea reframes something important. Reality is not static, it is active. And existence is something that happens, not something that simply is. Why intelligence might be rare or inevitable. Look out into the universe and you see silence, billions of galaxies, trillions of stars, and no clear signs of intelligence beyond Earth. This raises a deep question. Is intelligence rare? Or are we simply early? One possibility is that intelligence is extraordinarily unlikely. Life may be common, but complex life may be rare. Intelligence requires stable environments, long timescales, multiple evolutionary bottlenecks. Miss any one of them, and complexity never reaches awareness. In this view, humanity is fragile, a statistical outlier, a brief flare of self-awareness in a mostly silent universe. Another possibility is more unsettling. Intelligence may be inevitable. Given enough time, energy, and structure, information systems naturally evolve toward greater complexity. Not by intention, but by selection. Systems that process information efficiently outcompete those that don't. Stars create energy gradients. Planets create chemistry. Chemistry creates feedback loops. Feedback loops create learning systems. Given enough attempts, some of those systems will look back and ask questions. The universe doesn't need to aim for intelligence, it just needs to allow it. So why the silence? Perhaps intelligence is short-lived. Technological civilizations may destroy themselves or fade before spreading far. Or perhaps intelligence does not advertise itself, or perhaps we are early, among the first. In a multiverse, all possibilities occur. Universes with no intelligence, universes filled with it, universes where it flickers briefly. We find ourselves in one where it exists long enough to wonder about its own rarity. This tells us something subtle. The universe does not guarantee minds, but it permits them, and permission may be the most it ever offers. Whether intelligence is rare or inevitable, it is not trivial. It requires an extraordinary alignment of law, chance, and time. And for now, in this small region of space-time, the universe is thinking, asking questions, trying to understand itself. The ultimate fate of intelligence is powerful, but it is not immortal. It depends on energy gradients, structure, and time, and none of those last forever. As the universe expands, stars burn through their fuel. New stars form more slowly. Old stars fade. Eventually, galaxies grow dark. Energy becomes harder to extract. The universe smooths itself out. This future is not hostile. It is indifferent. A slow leveling. For intelligence to persist, it must adapt to diminishing resources. It must become more efficient, more patient, more subtle. Civilizations may stretch their thoughts across millennia. They may slow themselves down to match a cooling universe, or they may compress themselves into smaller and smaller physical systems. Some theories suggest intelligence could migrate from stars to black holes. Black holes are not just sinks of destruction. They are thermodynamic objects. They have temperature, entropy, information. In the far future, they may be the last usable sources of structure. Other possibilities are quieter. Intelligence may simply end, not with catastrophe, but with exhaustion. When no gradients remain, computation stops. Thought stops. Experience dissolves. This is not tragic in a cosmic sense. The universe does not mourn. But from inside intelligence, it matters deeply. And yet, something subtle remains. Even if intelligence ends locally, the universe itself continues. And in a multiverse, there are always other regions, other timelines, other beginnings. Intelligence may not be eternal, but it may be recurring, appearing wherever conditions allow, fading where they don't. Not a permanent feature of reality, but a repeating one. In that sense, Intelligence is like a wave on the surface of physics, temporary, local, but real, and when it exists, it carries something unique, perspective. What remains when all explanations end at some point? Every chain of explanation stops. Not because we give up, but because we reach the edge of what explanations can do. Physics explains how states follow from other states. It explains patterns, regularities, constraints, but it does not explain why those constraints exist at all. Why these laws? Why any structure? Why anything instead of nothing? These questions may not have answers in the way we usually mean answers. They may be category mistakes, or they may point to limits not of intelligence, but of explanation itself. This is where physics becomes quiet, not mystical, just silent. What remains is not ignorance, it's acceptance of scope. The universe is not obligated to make itself fully transparent. And yet, something astonishing remains. Despite all limits, the universe allows islands of clarity, moments where reality lines up just enough to be understood. Understanding does not conquer the universe. It does not reduce it. It briefly touches it. You are not meant to hold the universe in your head. No mind could, but you can hold fragments, patterns, stories, and those fragments are not meaningless. They are the universe learning about itself from one particular angle. In the end, there may be no final theory, no ultimate explanation, no last word, but there is this, a universe vast enough to generate questions, and within it, minds fragile enough to care about the answers. That may not be everything, but it is something. And sometimes, something is enough. The universe from the inside throughout this journey. We've spoken about the universe as if we were standing outside it. We've described its laws, its beginnings, its possible endings. But there is something quietly misleading about that perspective. Because we are not outside the universe. We are inside it. Every thought you've had while listening to this is a physical process. Neurons firing, energy flowing, information transforming. The universe is not something you are observing from afar. It is something you are participating in. When physics describes reality, it does so from a detached viewpoint. Equations don't feel awe. They don't experience time. They don't wonder what comes next. But the beings who write the equations do. This creates a strange loop. The universe produces minds. Those minds study the universe, and the universe through them becomes aware of its own structure. Not completely, not objectively, but locally. From the inside, reality feels continuous. Moments flow, memories accumulate, meaning emerges. From the outside, if such a view were possible, everything might already exist at once. A static structure of space-time. Both views can be true. They are not contradictions. They are perspectives. This is why physics alone never feels complete. Not because it's wrong, but because it deliberately leaves out experience. And experience is the only way reality is ever known. You never encounter equations directly. You encounter light, sound, memory, emotion. Physics explains the structure beneath those experiences, but it does not replace them. From inside the universe, time matters, choice matters, care matters. Even if, at a deeper level, everything follows impersonal laws. This does not cheapen experience, it grounds it. Meaning doesn't float above physics, it arises within it. And perhaps that is the most important shift. The universe is not a cold machine occasionally interrupted by life. Life is one of the things the universe does. What it means to be here at all at the end of all theories, there is a simple fact that remains. You are here. Out of countless possible universes, countless timelines, countless ways reality could have unfolded, there is this one, this moment, this awareness. Physics can tell you how improbable that is, how many conditions had to align, how narrow the window had to be, but it cannot tell you what it feels like. to be aware, to notice time passing, to care whether something matters. You are not guaranteed by the universe. You are permitted by it. And permission is fragile. Nothing in physics says there must be observers. Nothing requires experience to exist. And yet, here it is. Brief, local, finite. That finiteness is not a flaw. It is what gives experience its weight. If moments were infinite, they would be empty. If meaning were guaranteed, it would be hollow. The universe does not give you purpose. It gives you conditions. What you do with them is not written into the laws. From a cosmic perspective, your life is small. From the inside, it is everything you will ever know. Both are true. The universe does not watch you. But through you, it briefly watches itself. Not with intention, not with judgment, just with awareness. And when that awareness fades, when stars die, when thoughts end, when entropy smooths everything out, it will not undo the fact that this moment happened, that experience existed, that the universe once asked questions. Physics does not promise meaning, but it allows moments where meaning can appear, and that may be the most honest conclusion a universe like this can offer. After all the questions, after all the theories, after all the equations, after every attempt to explain where the universe came from and where it might be going, something remains, not a fact, not an answer, a state. Physics takes us very far. It tells us how matter behaves, how time flows, how space stretches, how stars ignite and fade. It tells us that reality is older than imagination, larger than intuition, and stranger than language. But eventually, physics reaches a point where it no longer moves forward, not because it fails, but because it has done what it can do. At that edge, there are no more equations to write, only consequences to live with. We learn that the universe does not revolve around us, that it is not arranged for comfort, that it does not pause for meaning. We learn that time will not stop for memory, that entropy will not reverse for love, that no structure lasts forever. And yet, this knowledge does not empty the universe. It deepens it, because understanding the scale of reality changes how small things feel, not smaller, but sharper, more precise, more fragile, more real. A moment is no longer just a moment when you know it cannot be repeated. A choice is no longer trivial when you understand branching realities and irreversible consequences. A life is no longer ordinary when you understand how unlikely it is. Physics does not tell you what to value, but it strips away illusions until what remains is honest. There is no cosmic guarantee that things will be fair, no promise that effort will be rewarded, no hidden balance sheet ensuring justice in the long run. And strangely, this makes care more meaningful, not less. Because care is no longer borrowed from eternity. It is generated locally, by beings who know things end. You begin to see the universe not as a story with a plot, but as a landscape, vast, unconcerned, open. And within that landscape, tiny regions where something unusual happens. Regions where matter organizes itself to remember, to anticipate, to feel. You are one of those regions, not because you were chosen, but because conditions allowed you to form. Your thoughts are not separate from the universe. They are events inside it, temporary reorganizations of energy and information. But temporary does not mean meaningless. Lightning is temporary, so are stars, so is light itself once it moves past you. The universe does not hold on to moments, but moments happen anyway. There is a temptation, when facing something this vast, to want reassurance, to want a final statement, a conclusion that wraps everything up and leaves nothing unresolved. But the universe does not conclude. It continues, and perhaps the most honest posture, after all this understanding, is not certainty, but attentiveness. To be here, without pretending it will last forever. To care without needing cosmic permission. To wonder without demanding closure. The universe may not have a reason for existing, but within it, reasons appear, briefly, quietly, locally. And when you look up at the sky, knowing what you now know, about entropy, about time, about scale, about chance, the stars do not lose their beauty. They gain depth. They are no longer decorations. They are processes, histories, futures. They are reminders that existence is not static, it is unfolding, and so are you. There may never be a final theory. There may never be an ultimate explanation. There may never be an answer to why this and not nothing, but there is this, a universe capable of producing questions, and within it, minds capable of holding them, even without answers. After all the questions, after all the theories, after everything physics can say, what remains is not silence. It is presence, and sometimes that is enough. Top of form, living inside an unfinished universe. After everything you've learned, the universe does not suddenly become solved. It becomes unfinished, and so do you. There is a subtle shift that happens once you truly accept the scale of reality. You stop expecting the universe to revolve around explanation. You stop waiting for a final answer that will settle everything, and instead, you begin to live inside uncertainty. This is not the same as confusion. Uncertainty in physics is not ignorance. It is structure. It is the space where multiple futures remain possible. It is what allows motion, change, and choice. A finished universe would be static, nothing left to ask, nothing left to explore, nothing left to become. But our universe is not like that. It is still unfolding. Stars are still forming, galaxies are still evolving, space is still expanding. Even now, regions of the universe are crossing horizons, becoming forever unreachable. Reality is not waiting. It is moving. And so are you. Your understanding today is not the understanding you will have tomorrow. Your perspective changes, not because truth changes, but because you move through it. Living inside an unfinished universe means accepting that clarity comes in layers. Some questions resolve, others deepen. Some answers close doors, others open new ones. This is how physics works. Each discovery does not simplify reality. It reveals more structure, more subtlety, more edge. The same is true of life. Knowing that time is finite does not make moments smaller. It sharpens them. Knowing that nothing is guaranteed does not empty meaning. It localizes. You stop waiting for permanence to justify care. You stop demanding that things last forever to take them seriously. In an unfinished universe, meaning is provisional, and that is not a weakness. It is what allows meaning to respond to circumstance, to growth, to loss. There is no cosmic authority monitoring whether your life aligns with the laws of physics in some deeper sense. The laws are already satisfied. They are silent. What remains is how you move through the structures they allow. How you treat time once you understand it flows one way. How you treat others once you understand they are as temporary as you. How you treat curiosity once you realize it never ends. The universe does not tell you how to live inside it. It only provides conditions, temperature gradients, energy flows, causal chains. Within those constraints, life improvises. You are not required to resolve the universe. You are not responsible for answering its deepest questions. Those questions existed long before you and will persist long after. Your task, if it can be called a task, is smaller and quieter. To notice, to participate, to add one thread of experience to a fabric far larger than yourself. An unfinished universe does not promise closure, but it allows continuity, moment following moment, choice following awareness. And perhaps that is the most realistic form of hope, not that everything will make sense one day, but that understanding will keep unfolding as long as there are minds capable of holding it. The universe is not complete, and neither are you. And that shared incompleteness is not a flaw. It is the condition that allows anything to happen at all. What we owe a temporary world, once you accept that everything is temporary, a quiet question emerges. Not a cosmic one, a practical one. What do we owe a world that will not last? The universe does not ask for stewardship. It does not require preservation. Stars explode without apology. Galaxies collide without regret. From a cosmic perspective, nothing is protected. But we are not cosmic perspectives. We are local ones, embedded in fragile systems that only work within narrow ranges. Air thin enough to breathe, water liquid long enough to drink, temperatures stable enough for life. A temporary world is not worthless. It is vulnerable, and vulnerability changes responsibility. Physics tells us that complexity is expensive. It requires energy, time, balance. Once disrupted beyond a threshold, it does not easily return. Life is not guaranteed to reappear once it is erased. Knowing this reframes care. Care is no longer about permanence. It is about continuity, about allowing patterns to persist long enough to matter to those inside them. You don't protect something because it will last forever. You protect it because it won't. A forest does not need to exist eternally to deserve preservation. A culture does not need to be infinite to deserve care. A person does not need cosmic importance to matter. In a temporary universe, value is not assigned from above. It is generated locally by beings who understand loss. Physics strips away illusions of destiny, but it sharpens ethics. Because when nothing is guaranteed, choices carry weight. You cannot defer responsibility to eternity. There is no later universe where consequences disappear. There is only this one, this configuration, this moment. A temporary world does not demand heroism. It asks for attention, for restraint where excess would collapse systems, for patience where haste would destroy fragile equilibria. The universe will not punish neglect, but life will, quietly, inevitably. What we owe a temporary world is not perfection. It is care proportional to fragility. Meaning as an ongoing practice. Meaning is often imagined as something discovered once and then kept, a truth found, a purpose revealed. But physics suggests something else. Meaning behaves less like an answer and more like a process. Nothing in the universe remains fixed. Stars evolve, systems drift, conditions change. Why would meaning be any different? Meaning does not sit waiting to be uncovered. It is constructed, maintained, and revised over time. This does not make it arbitrary. It makes it responsive. Meaning adapts to circumstance, to loss, to growth, to understanding. In a universe governed by entropy, anything that persists must be actively sustained. Meaning is no exception. You practice it the way you practice attention, the way you practice care, the way you practice honesty in the face of uncertainty. There is no final meaning that survives every possible future, but there are meanings that survive long enough to guide action now. Raising a child, learning something difficult, showing restraint when power allows excess, choosing patience over certainty. These are not cosmic acts. They are local alignments between understanding and behavior. Physics does not judge them, but it allows them, and allowance is all they require. Meaning does not need the universe to agree with it. It only needs to be lived, repeatedly, imperfectly. In that sense, meaning is less like a destination and more like a stance, a way of standing inside uncertainty without collapsing into indifference. You do not need to resolve the universe to live meaningfully within it. You only need to recognize that experience is finite and act accordingly. A practice of meaning does not deny impermanence. It works with it. It treats time as precious because it runs out. And perhaps that is the most grounded conclusion physics offers. Not that life has a hidden purpose, but that purpose is something temporary beings can practice inside a temporary world. Why hope still makes sense. Hope often gets misunderstood. People imagine it as denial, a refusal to see reality as it is. But that kind of hope is fragile. It collapses the moment facts intrude. The hope that survives physics is something quieter. Physics tells us the universe does not bend to desire. It does not guarantee progress. It does not protect outcomes. It does not ensure that effort leads to reward. And yet, hope persists, not because the universe promises anything, but because possibility still exists. Hope is not the belief that things will turn out well. It is the recognition that outcomes are not fixed in advance, that the future is not fully written, that present actions still influence which paths become real. Even in a universe governed by law, there is room for contingency. Small differences matter, initial conditions propagate. Tiny changes can reshape futures. This is not romantic, it is physical. Entropy increases, yes, but local decreases are allowed as long as energy flows. Stars form, life organizes, order appears temporarily. Hope lives in these temporary gradients. To hope, then, is not to deny entropy. It is to work within it, to build structures that persist for a while, to create meaning that lasts long enough to be experienced. Hope does not require certainty. It requires openness, a refusal to collapse possibility prematurely. In this sense, hope is an intellectual stance. It says, the future is constrained, but not closed. You can know the universe will end, and still care about what happens before that. You can know everything is temporary and still choose to act as if moments matter. Because they do. Hope is not optimism. It is endurance, the willingness to continue even when permanence is impossible. And perhaps this is why hope feels stubborn, why it survives knowledge instead of being erased by it. It is not borrowed from cosmic guarantees. It is generated locally by beings who understand limits and act anyway. Hope makes sense because uncertainty remains. And as long as uncertainty exists, so does choice. Letting the universe be larger than us, there is a temptation when trying to understand the universe to make it fit us, to reshape it into something comforting, something familiar, something that mirrors our values. Physics resists this relentlessly. The universe is larger than our stories about it, larger than our fears, larger than our hopes, larger than our need for closure. Letting the universe be larger than us is not resignation. It is release. It means giving up the demand that reality justify itself in human terms, that it explain why suffering exists, why injustice occurs, why things end. Physics does not answer those questions, and forcing it to only creates distortion. When you let the universe be what it is, impersonal, vast, law-governed, something unexpected happens. You become lighter. You stop taking cosmic indifference personally. You stop interpreting randomness as judgment. You stop needing the universe to agree with you before you act. Humility, here, is not self-erasure. It is perspective. You realize you were never meant to carry the universe on your shoulders. You are not responsible for fixing existence. You are responsible for how you behave inside the slice of reality you inhabit. Letting the universe be larger than us also frees wonder. When you no longer expect reality to conform to expectation, strangeness becomes a feature, not a threat. Black holes can exist without needing to symbolize anything. Time can flow one way without being moral. Entropy can increase without being cruel. And within all that impersonality, life still appears, care still appears, attention still appears. You do not need the universe to revolve around meaning for meaning to exist. Meaning does not compete with cosmic scale. It occupies a different layer entirely. Letting the universe be larger than us means accepting that we are not the point, but we are points. Moments where something rare happens, awareness. And perhaps that is the most balanced stance of all. not shrinking the universe to fit human comfort, not shrinking humans to nothing, but allowing both to coexist at their proper scales. The universe can be vast, indifferent, unfinished, and within it, you can still live carefully, hope realistically, and mean something locally. Responsibility without cosmic permission. For a long time, responsibility was tied to belief in oversight, a higher order, a final judgment, a cosmic balance sheet. But physics removes that comfort. The universe does not watch. It does not keep score. It does not reward alignment or punish neglect. This can feel destabilizing. If nothing is watching, why care? If there is no ultimate arbiter, why act responsibly? But responsibility does not require permission. It does not need endorsement from the structure of reality. Responsibility emerges whenever actions have consequences for conscious beings. Physics tells us something very clear: causes propagate, effects persist, choices alter trajectories. You do not need a universe that cares for consequences to be real. You only need systems sensitive enough to be affected. People, ecosystems, institutions, futures. Responsibility without cosmic permission is heavier, but also more honest. It cannot be deferred upward. It cannot be outsourced to fate. When you understand that entropy increases, you understand that damage accumulates. When you understand that time only moves forward, you understand that harm cannot be undone. When you understand scale, you understand how small actions compound over time. This does not mean paralysis. It means precision. You stop asking, what does the universe want? And start asking, what does this situation require? Responsibility becomes local, contextual, specific. You are not responsible for everything. You are responsible for what you influence, what you touch, what you choose when alternatives are available. This kind of responsibility is quiet. It does not announce itself. It does not feel heroic. It often feels inconvenient. But it is grounded. It aligns with physics rather than defying it. No law of nature guarantees justice, but justice can still be practiced. No equation mandates care, but care can still be chosen. Responsibility without cosmic permission is not about saving the universe. It is about not adding unnecessary harm to a fragile system that did not ask to exist. And perhaps that is the deepest form of maturity. A finite universe allows a quiet kind of courage. Courage is often imagined as something loud, defiant, dramatic, visible. But in a universe like ours, the most durable courage is quiet. It is not the courage of certainty. Physics does not allow that. It is the courage of continuation, to live without guarantees and still invest, to understand impermanence and still care, to know that everything ends and still begin. This kind of courage does not come from belief that things will work out. It comes from acceptance that they might not. Quiet courage is waking up in a universe that does not promise meaning and choosing to live as if meaning can be made. It is continuing to learn, even when knowledge destabilizes comfort. It is refining ethics, even when the universe does not enforce them. It is choosing honesty over illusion, without collapsing into despair. This courage does not need witnesses. It is not performative. It does not announce itself with conviction or slogans. It shows up as patience, as restraint, as refusing to simplify reality for the sake of emotional ease. It is the courage to hold two truths at the same time, that nothing is guaranteed, and that what you do still matters. In a universe governed by probability, acting well is never assured of success, but action still shapes probability, still shifts distributions, still changes which futures occur. Quiet courage understands this. It does not demand certainty before acting. It does not wait for reassurance. It recognizes that meaning is fragile and treats fragility as something worth protecting, not dismissing. This courage does not fight the universe. It works with it, within constraints, within time, within uncertainty, And perhaps that is the most grounded form of bravery a lawful, indifferent cosmos allows. Not defiance, not surrender, but participation. To live carefully, to think clearly, to care locally, to act knowing the outcome is never fully known. In a universe that does not promise anything, this quiet courage may be the most honest strength there is. What it means to finish without closure, most stories train us to expect closure. A final revelation, a resolved conflict, a clear answer that settles everything. But the universe does not work that way, and neither does honest understanding. Physics teaches us that many processes do not end cleanly. They asymptotically approach limits. They fade, they thin out, they don't stop, they lose definition. The expansion of the universe does not conclude, it continues. Entropy does not finish increasing, it approaches equilibrium. Time does not arrive at a final moment. It dissolves into irrelevance. So when we reach the end of a long inquiry, what we reach is not an answer. It is a boundary condition. A place where questions stop producing sharper explanations and begin producing perspective. Finishing without closure means accepting that understanding has edges, not sharp edges, but soft ones. Regions where further questions exist, but no longer clarify action or insight. This is not failure, it is maturity. A child asks questions because the world is unknown. An expert asks questions because the world is partially known. A wise position asks fewer questions, not because curiosity dies, but because it learns which questions matter now. Physics teaches us that some things are undecidable, not temporarily, permanently, because information cannot reach us, because measurement disturbs systems, because explanation runs out of traction. Closure, in such a universe, would be dishonest. It would pretend that uncertainty can be eliminated rather than lived with. So to finish without closure is to stop demanding more from reality than it can give. It is to say, this is far enough for now. Not forever, not absolutely, but enough to act wisely within the slice of reality we inhabit. The desire for closure often comes from discomfort, from wanting the universe to feel safe, resolved, complete. But safety does not come from final answers. It comes from learning how to move without them. Finishing without closure is not walking away. It is standing still long enough to recognize that the horizon does not need to be crossed to orient yourself. You do not need to know everything to live coherently. You only need to know enough to avoid unnecessary harm, to preserve what is fragile, and to remain responsive to change. A universe that never fully closes its questions is not broken. It is alive, carrying the questions forward at the end of inquiry. Questions do not disappear. They change roles. Early on, questions demand answers. Later, they become companions. They walk with you instead of pulling you forward. You stop asking what is the universe ultimately for, and start asking, what does this moment require of me? You stop asking, will everything turn out okay? And start asking, what can I do, given that nothing is guaranteed? These questions are quieter. They don't seek cosmic validation. They seek alignment between understanding and action. Physics gives us a particular kind of humility. It shows us how small we are without telling us we are irrelevant. It shows us how temporary everything is without telling us to despair. Carrying questions forward means allowing wonder without demanding comfort. It means letting curiosity remain open-ended, not as restlessness, but as attentiveness. The best questions do not paralyze. They refine perception. They sharpen care. They prevent arrogance. A person who understands scale does not rush to certainty. A person who understands entropy does not waste what is delicate. A person who understands time does not postpone what matters. These are not philosophical positions. They are practical consequences of understanding reality as it is. You do not carry the universe forward. You carry your relationship to it, your way of standing inside uncertainty, your tolerance for complexity, your refusal to simplify what should not be simplified. Questions, when carried well, do not destabilize life. They stabilize it. They prevent false absolutes. They keep meaning flexible. And perhaps this is the most enduring outcome of all this inquiry, not knowledge, not answers, but a posture, a way of moving through a universe that is vast, indifferent, unfinished, without shrinking it or inflating yourself. You carry the questions forward not to solve them, but to let them shape how you listen, how you choose, and how you care. And that, in a universe that never promised clarity, may be the most faithful way to continue. Letting meaning be local, one of the quiet lessons physics teaches, is that not everything needs to be universal to be real. For a long time, humans searched for meaning that would hold everywhere. A rule written into the universe itself, a purpose stamped onto existence, a reason that applied equally to galaxies and to grief. Physics dissolves that expectation. It shows us a universe governed by laws, not intentions, by constraints, not narratives. At first, this feels like loss. If meaning isn't universal, is it fragile? If it isn't guaranteed, can it be trusted? But locality does not weaken reality, it defines it. Temperature is local, pressure is local, life is local. Meaning fits the same pattern. It arises where conditions allow it. A conversation matters because two people are present. A memory matters because someone carries it. A promise matters because it shapes future behavior. None of these require cosmic permanence. They require context. Letting meaning be local frees it from impossible expectations. It no longer has to justify itself to the entire universe. It only has to be coherent within the lives it touches. This is not a retreat. It is a correction. A star does not need to illuminate the entire cosmos to be real. A life does not need to matter forever to matter fully. Physics shows us that the universe is built from local interactions. Forces weaken with distance. Influence decays. Causality has range. Meaning follows the same architecture. When you accept this, you stop asking meaning to do work it was never meant to do. You stop demanding that it answer why suffering exists everywhere. You let it answer how to act here. Local meaning is precise. It responds to circumstance. It adjusts to understanding. It can change without collapsing. And because it is local, it can be shared, passed from person to person, sustained through practice rather than belief. The universe does not carry meaning forward. People do. Briefly, imperfectly, enough. The multiverse as a consequence, not an idea. When physicists talk about the multiverse, they are often misunderstood. It is not usually proposed because it feels exciting or because it sounds philosophical. In fact, many physicists are uncomfortable with it. The multiverse appears not as an invention, but as a consequence. The story begins with equations that work too well to ignore. Quantum mechanics predicts experimental outcomes with astonishing precision. Inflationary cosmology explains the large-scale structure of the universe better than any competing theory. And when physicists follow these frameworks without adding extra assumptions, they repeatedly encounter the same result. Reality does not remain singular. In quantum mechanics, a system does not evolve toward one outcome. It evolves toward many possible outcomes at once. The mathematics does not select one. It describes a superposition. To recover a single experienced result, something extra must be added, or something radical must be accepted. One option is collapse, a mysterious, unobservable process that selects a single outcome. Another option is the many worlds interpretation, first proposed by Hugh Everett III. In this framework, nothing collapses. all outcomes occur. They simply stop interacting. The universe does not split explosively. There is no dramatic branching event. Instead, quantum systems become decoherent. Information about outcomes spreads into the environment. Interference becomes impossible. Each outcome evolves independently. From inside one branch, it feels like randomness. From the outside, if such a perspective even makes sense, the evolution is deterministic. The multiverse here is not optional. It is the most literal reading of the quantum equations. Cosmology leads to a similar place. Inflation explains why the universe is flat, smooth, and homogeneous. But many inflation models predict that inflation never fully ends. It stops locally, forming bubble universes. Elsewhere it continues. This produces an inflationary multiverse. Each bubble has its own space-time, its own initial conditions, potentially its own physical constants. Our observable universe would be one bubble among countless others. Again, this is not added to explain fine-tuning. It arises naturally once inflation is allowed to run indefinitely. Removing the multiverse often requires more assumptions than keeping it. This is why the multiverse is so controversial, not because it is wild, but because it is difficult to avoid. It forces physicists to confront a difficult question: what counts as science when direct observation is impossible? The multiverse challenges the traditional boundary between physics and philosophy, but it does so from inside physics, not from outside it. And this leads to a crucial realization. The multiverse is not one theory. It is a family of consequences arising from different well-supported frameworks: quantum theory, cosmology, string theory. Each points toward multiplicity in its own way. The discomfort many feel is not about evidence. It is about implication. Because if the multiverse is real, then our universe is not unique. And uniqueness has been central to how humans understand meaning. What the multiverse explains, and what it does not. Once the multiverse is on the table, it immediately seems to explain a great deal. But good physics requires restraint, so we must be precise about what the multiverse can explain and what it cannot. One of the strongest motivations for multiverse thinking is the problem of fine-tuning. Many physical constants appear delicately balanced. Change them slightly and stars would not form. Chemistry would collapse. Complex structures would be impossible. In a single universe picture, this looks improbable. It invites explanations involving necessity, design, or unknown principles. In a multiverse, fine-tuning becomes selection. If many universes exist with many different constants, then most are sterile. Observers can only arise in the rare regions where conditions allow complexity. This is known as anthropic selection. It does not explain why the constants exist. It explains why we observe the ones we do. This is subtle but important. The multiverse does not claim these constants exist because life needs them. It says, if constants vary, observers will find themselves where observation is possible. The same logic applies to the arrow of time. Low entropy beginnings are rare, but in a vast multiverse, rare conditions occur somewhere. Only in those regions can time have a direction and memory exist. The multiverse also offers a framework for understanding why physical laws might appear simple yet contingent. In theories like string theory, there are enormous numbers of mathematically consistent vacuum states. This collection is often called the landscape. Each vacuum corresponds to a universe with different laws. Again, the multiverse does not explain why the landscape exists. It explains why we occupy one region of it. But now we reach the limits. The multiverse does not explain why there is something rather than nothing, why the underlying mathematical structure exists, why the laws take the form they do at the deepest level. These questions remain open. The multiverse also does not imply communication between universes, travel between branches, access to other versions of oneself. Those ideas belong to fiction, not physics. Crucially, the multiverse does not eliminate meaning. It reframes it. Meaning becomes indexical. It depends on where you are, which branch you inhabit, which history you experience. Your experiences matter because they are yours. Not because they are unique across all reality, but because experience is always local. The multiverse does not cheapen life. It removes cosmic favoritism. And what remains is responsibility without privilege, care without centrality. From a physics standpoint, the multiverse is neither comforting nor threatening. It is simply what the math suggests when taken seriously. Whether it is ultimately correct remains unknown. But its value is already clear. It forces us to be precise about explanation, observation, and meaning. And perhaps that is its deepest contribution. The multiverse does not answer our oldest questions. It clarifies which questions physics can ask and which ones must remain open. Identity in a multiverse. What does you mean? One of the most unsettling consequences of the multiverse is not cosmological. It is personal. If many universes exist, or many branches of the same universe, what does that mean for identity? What does you refer to? In everyday life, identity feels continuous. You remember the past. You anticipate the future. You feel like a single thread moving through time. Physics does not deny this experience, but it reframes it. In the many worlds interpretation of quantum mechanics, when a quantum event has multiple outcomes, each outcome corresponds to a different branch of reality. Crucially, you are part of the quantum system, so when branching occurs, there is not one future version of you. There are many. This sounds alarming, but the physics is subtle. Branching does not produce copies that later diverge. It produces divergence from a shared past. Up to the moment of branching, there was a single physical history. Afterward, there are multiple non-interacting continuations. Each future version of you has the same memories, the same personality, the same internal sense of continuity from the inside. Nothing feels fragmented. Each version experiences itself as the only one. This reveals something important. Identity in physics is branch relative. It does not refer to a unique trajectory across all reality. It refers to a specific sequence of experiences within one branch. This is not unique to the multiverse. Even in a single universe picture, identity is already approximate. Your atoms change. Your brain rewires. Your memories degrade. Continuity is not material. It is informational. The multiverse simply makes this explicit. Identity is not about being singular across reality. It is about being coherent within experience. This has consequences for responsibility. Each version of you is responsible for the outcomes it experiences. No version gets credit for what happens in other branches. No version escapes consequences because alternatives exist elsewhere. The multiverse does not dissolve agency. It localizes it. From a physics perspective, there is no true you spread across branches. There are many legitimate continuations of the same past observer, each equally real, each equally grounded in physical law. This is uncomfortable because human intuition evolved in a world that appeared singular. But discomfort does not imply inconsistency. The mathematics remains clean. The deeper lesson is this. Physics does not privilege narratives. It describes structure. And identity, in a multiverse, is a structure that persists locally, not globally. Probability, observation, and why you see this universe if all outcomes occur in the multiverse. What does probability even mean? Why do we say one outcome is likely and another is rare? This is one of the hardest technical problems in multiverse physics, and it is still actively debated. In ordinary probability, we imagine uncertainty about which outcome will occur, but in a multiverse, all outcomes occur. So probability cannot mean chance of existence. It must mean something else. In quantum mechanics, probability is encoded in the amplitude of the wave function. The square of this amplitude gives the Born rule, the rule that predicts experimental frequencies. In a many worlds picture, the Born rule does not say which outcome happens. It says how much weight each branch carries. Branches with larger weight contain more observer moments, are statistically more common, are more likely to be experienced by a randomly sampled observer. This reframes probability as self-location uncertainty. Before an observation, you are uncertain which branch you will find yourself in. Afterward, you learn where you are. This is not philosophical wordplay. It is a precise shift in meaning. Probability becomes a measure of which experiences are typical. This same logic appears in cosmology. If a multiverse contains many universes with different properties, then observation is conditioned on existence. You cannot observe a universe that does not allow observers. This is called observer selection. It is not a bias, it is a constraint. You observe this universe because only universes like this can be observed. This does not explain why the universe exists. It explains why this kind of universe is what you see. This idea is often misunderstood as circular. But it is no more circular than saying, fish observe water, because without water, fish cannot exist. The multiverse does not predict that observers are special. It predicts that observation is conditional. This also explains why we find ourselves in a universe with long-lived stars, stable chemistry, and a long arrow of time. These conditions are not typical, but observers are not typical samples of all reality. They are typical samples of observer-supporting regions. Probability, then, is not about fate, it is about typicality, about what experiences are common among those that exist at all. This is a quiet but profound shift. The universe does not select outcomes. Observers find themselves in outcomes that support observation. And that is why, in a vast multiverse, this universe does not feel random. It feels structured, coherent, lawful. Not because it had to be this way, but because only such worlds can be noticed. Can the multiverse be tested? Science at the edge, the strongest criticism of the multiverse, is not emotional or philosophical. It is scientific. Can it be tested? Science is built on observation. A theory earns its place by making predictions that can be checked against reality. If a theory cannot, even in principle, be confronted with evidence, its status becomes uncertain. At first glance, the multiverse seems to fail this test. Other universes are, by definition, outside our observable horizon. No light from them reaches us. No signal can cross the boundary. So how could physics ever say anything meaningful about what lies beyond? But this is not the first time physics has faced such a problem. Atoms were once unobservable. Black holes were once mathematical curiosities. Gravitational waves were once thought undetectable. In each case, physics advanced indirectly, not by seeing the object itself, but by seeing its effects. The same strategy applies to the multiverse. Physicists do not look for other universes directly. They look for imprints. In inflationary multiverse models, our universe formed as a bubble within a larger inflating space. If other bubbles formed nearby in the early universe, they could, in principle, have collided with ours. Such collisions would not destroy the universe. They would leave subtle patterns. Specifically, they could leave unusual temperature, anisotropies, circular features, statistical anomalies in the cosmic microwave background, the afterglow of the early universe. So far, no conclusive evidence has been found. Some anomalies exist. None are decisive. But the key point is this: the multiverse is not completely disconnected from observation. It is weakly constrained, not metaphysically isolated. Another avenue is theoretical consistency. If a theory that is testable inevitably implies a multiverse, then rejecting the multiverse means rejecting the underlying theory. This is exactly the situation with certain versions of inflation and quantum mechanics. The multiverse is not added. It appears when we refuse to add extra assumptions just to preserve uniqueness. This creates a tension in science. Do we restrict theories to what is directly testable, or allow theories whose core is testable, even if some consequences are not? There is no consensus. Some physicists argue that testability must remain absolute. Others argue that indirect inference is legitimate when grounded in well-tested frameworks. This debate is ongoing, and importantly, it is not settled by preference. It will be settled by future theoretical and observational progress. The multiverse is not unscientific, but it is science under strain. It pushes the methodology of physics to its limits. Why many physicists resist the multiverse, even among experts? The multiverse is deeply controversial, not because it is incoherent, but because of what it changes. For centuries, physics aimed to explain why the universe is the way it is. One set of laws, one outcome, one reality. The multiverse challenges that ambition. It suggests that some features of reality may not have deep explanations. They may be contingent, accidental, environmental. Many physicists find this unsatisfying. It feels like giving up, like replacing explanation with resignation. For example, if physical constants vary across universes, then asking why do they have these values may have no deeper answer than because we are here. This feels dangerously close to abandoning the search for fundamental laws, and that worry is legitimate. But proponents respond carefully. They argue that the multiverse does not end explanation, it relocates it. Instead of asking, why this universe? We ask, why this space of possibilities? Why these equations? Why this landscape of laws? The multiverse does not remove mystery. It moves it one level deeper. Another resistance comes from probability. If infinitely many universes exist, how do we define what is typical? How do we regulate infinities? How do we avoid paradoxes? These are real technical problems, not philosophical hand-waving. Entire research programs are devoted to defining measures, cutoffs, and consistency conditions in multiverse cosmology. There is also a cultural resistance. Physics has always prized economy, simplicity. The multiverse feels extravagant, wasteful, too much reality. But physics does not optimize for aesthetics. It follows mathematics and evidence. Nature has no obligation to be minimal. Historically, reality has often turned out to be larger than expected. More stars, more galaxies, more particles, more structure. The multiverse may be another such expansion, or it may be wrong. What matters is this: the debate is not between science and fantasy. It is between different standards of explanation within science itself. That makes the multiverse one of the most important ideas in modern physics, even if it turns out to be false. Because it forces physicists to clarify what counts as explanation, what counts as evidence, and how far science can go in that sense. The multiverse is already doing valuable work, not by answering everything, but by revealing the boundaries of scientific reasoning, and those boundaries matter. Because knowing where knowledge ends is itself a form of understanding. Time across the multiverse, many clocks. No master clock. One of the most misunderstood ideas about the multiverse is the assumption that it all happens in time, the way we experience time. But physics does not support a single universal clock. There is no master timeline against which all universes tick. In relativity, time is already local. Different observers experience time differently depending on motion and gravity. There is no absolute now, even within one universe. The multiverse takes this idea further. In inflationary multiverse models, different universes do not share a common beginning. They do not form simultaneously. They do not age together. Each universe has its own space-time, its own internal notion of past and future. Asking what time is it in the multiverse is like asking what direction is up in the entire cosmos. The question assumes a structure that does not exist. In the many worlds interpretation, time also behaves differently than intuition suggests. Branching does not occur at moments in a global timeline. It occurs through decoherence, a gradual physical process where correlations spread into the environment. There is no precise instant where one universe becomes many. No sharp split. Only increasing separation between outcomes that can no longer interfere. This means the multiverse does not evolve like a tree growing forward in time. It evolves like a structure of correlations within spacetime. From inside a branch, time feels linear. From the mathematical description, all branches coexist within the same formal structure. Some physicists describe this using the block universe picture. In this view, past, present, and future all exist as part of a four-dimensional spacetime. The multiverse extends this idea. Instead of one spacetime block, there may be many. But crucially, this does not eliminate experience. Even if all moments exist mathematically, conscious observers still experience time sequentially. Memory points one way. Entropy increases. Causality holds locally. So the multiverse does not erase the arrow of time. It multiplies it. Each universe carries its own arrow, rooted in its own low-entropy past. This has a profound implication. There is no cosmic moment where everything happens at once. No final snapshot of all reality. The multiverse is not a movie playing on a universal screen. It is a collection of locally ordered histories with no global synchronization. Time, then, is not a background for the multiverse. It is a property within each universe, and that makes our experience of time neither privileged nor illusory. It is simply local. Meaning in a multiverse. Why nothing is diluted, a common reaction to the multiverse is a sense of dilution. If countless universes exist, if countless versions of events unfold, does anything still matter? Physics gives a clear answer. Yes, but not in the way we once thought. Meaning does not come from uniqueness across all reality. It comes from experience, and experience is always local. Even in an infinite multiverse, no observer experiences infinity. You experience one sequence of moments, one history, one set of consequences. That is not reduced by the existence of others elsewhere. Consider a simple analogy. There are billions of stars in the galaxy. That does not make the sun less important to Earth. Its significance is not cosmological, it is contextual. The multiverse works the same way. Your life does not need to be the only one of its kind to matter fully. It only needs to be lived. From a physics perspective, nothing in the multiverse framework allows value to leak between branches. There is no averaging of meaning, no cosmic ledger that sums lives together. Each branch is dynamically isolated. Each carries its own causal story. This means responsibility remains intact. Care remains intact. Loss remains real. If something matters to conscious systems, then it matters, regardless of what happens elsewhere. Physics does not discount experience because it is replicated. In fact, the multiverse sharpens this truth. It shows that meaning is not stamped onto the universe from above. It emerges wherever awareness exists. This removes the last illusion of cosmic favoritism. There is no central universe, no chosen timeline, no privileged observer. And paradoxically, this makes each observer more grounded, not more important, but more real within their context. In a multiverse, meaning does not scale with size. It scales with connection, with memory, with consequence. This also explains why the multiverse does not undermine ethics. Ethics are about effects on conscious systems. Those effects do not disappear because other branches exist. If anything, the multiverse removes excuses. You cannot appeal to destiny. You cannot appeal to uniqueness. You can only appeal to what happens here as a result of this action. So the multiverse does not flatten meaning. It localizes it completely. And locality, in physics, is not weakness. It is how reality works. The final lesson of the multiverse is not that nothing matters. It is that nothing matters everywhere. But some things matter here, and here is all experience has ever needed. The multiverse and the limits of explanation, one of the most important lessons the multiverse teaches, has nothing to do with how many universes exist. It has to do with how explanation itself works. In traditional physics, explanation followed a familiar pattern. If something seemed unlikely, we searched for a deeper law. If a value looked fine-tuned, we assumed there must be a reason. If outcomes varied, we looked for hidden variables. The multiverse disrupts that expectation. It introduces the idea that some features of reality may not have deeper explanations within the universe itself. They may be environmental. In a multiverse, asking why does this universe have these properties is like asking why does Earth have this particular climate. There is an answer, but it is not fundamental. It depends on location. This does not mean explanation ends. It means explanation changes levels. Instead of asking, why this outcome, we ask, why this space of possible outcomes? Physics still seeks deep structure, but it becomes more careful about what kind of answers are possible. The multiverse teaches us that not every observed fact must be traced to a unique cause. Some facts are selection effects. They arise because observers can only exist under certain conditions. This is uncomfortable because it feels like losing control. It challenges the idea that physics will eventually answer every why question. But this discomfort is not new. Relativity taught us that space and time are not absolute. Quantum mechanics taught us that certainty is not fundamental. The multiverse teaches us that uniqueness may not be fundamental either. Each step reduced our intuitive sense of order, but each step increased the accuracy and coherence of our theories. The multiverse may be another such step, or it may be a sign that our current theories are incomplete. Both possibilities are taken seriously. What matters is intellectual honesty. Physicists do not claim the multiverse is confirmed. They claim that, given what we know, it is a plausible consequence of otherwise successful frameworks. This places the multiverse at the edge of explanation, not beyond science, but at its boundary. And boundaries matter. They tell us where inference remains reliable and where humility is required. If the multiverse is real, then explanation does not end, but it becomes layered. Local laws govern local phenomena. Global structure governs which laws appear where, and beyond that, there may be no further why at all. This is not failure, it is recognition of scope. Physics does not promise that reality will be fully intelligible. It promises something more modest and more reliable, that we will know how far understanding can go. The multiverse as a mirror, not a message in the end. The multiverse does not arrive as a message from the universe. It arrives as a mirror. It reflects our assumptions about explanation, importance, and meaning. For centuries, humans assumed the universe must be centered, unique, and purposeful, not because evidence demanded it, but because perspective encouraged it. Each expansion of scale challenged that view. Earth was not the center. The sun was not special. The galaxy was not unique. And now, perhaps, the universe itself is not singular. The multiverse does not say that we are insignificant. It says that significance is not cosmic by default. It is contextual. This is not a demotion. It is clarification. The multiverse does not tell us what to value. It tells us that value does not come from rarity across reality. It comes from experience, memory, and consequence. If many universes exist, that does not erase what happens in this one. Causality remains intact. Pain remains real. Care remains necessary. The multiverse does not weaken responsibility. It removes metaphysical excuses. You cannot appeal to destiny. You cannot appeal to cosmic selection. You can only appeal to what actions do here. In this sense, the multiverse aligns with everything physics has taught us before. Reality is lawful, impersonal, unconcerned. And yet, within it, complex systems arise that can care. The multiverse does not override that fact. It highlights it. If anything, it makes conscious experience more remarkable. Not because it is unique across all existence, but because it emerges at all in a universe governed only by laws and chance. The multiverse does not ask to be believed. It asks to be understood carefully and held lightly. It may be real. It may be wrong. But either way, it teaches us something enduring, that the universe does not need to revolve around us for our lives to matter. Physics does not give us a final story. It gives us a framework for asking better questions and recognizing which answers are available. The multiverse is one such question. Large, unsettling, incomplete. And like the universe itself, it does not conclude. It invites restraint, precision, and humility. If this is where the story ends, it ends honestly, with understanding extended as far as evidence allows, and with curiosity intact beyond that boundary. The future of multiverse physics, what comes next. The multiverse is not a finished theory. It is not a settled conclusion. It is a working consequence of ideas that are still evolving. And that means its future is open. In physics, ideas survive not because they are dramatic, but because they remain useful. They guide calculation, they suggest experiments, they organize confusion. The multiverse is currently in this intermediate state, not confirmed, not dismissed, actively tested at the edges. One direction forward comes from cosmological observation. Future measurements of the early universe will be far more precise than anything we have now. New generations of space telescopes and detectors will map the cosmic microwave background with unprecedented resolution. Physicists are not looking for proof of other universes. They are looking for consistency. If inflationary models continue to match observations while inevitably predicting eternal inflation, then the multiverse becomes harder to ignore. Rejecting it would mean rejecting otherwise successful theories. Another path forward is quantum foundations. The many worlds interpretation is not universally accepted, but alternative interpretations of quantum mechanics come with their own costs. Some add collapse mechanisms, some add hidden variables, some modify the equations themselves. Future experiments in quantum information, especially involving large, complex systems, may constrain which interpretations remain viable. If collapse never appears, even in increasingly macroscopic systems, then branching without collapse becomes the simplest explanation, not the strangest. The simplest, a third direction, is theoretical unification. Any successful theory of quantum gravity will need to reconcile spacetime, entropy, and information. So far, every serious attempt has pointed toward a picture where spacetime is not fundamental. And when spacetime stops being fundamental, multiplicity becomes natural. The multiverse may ultimately disappear, not because it is wrong, but because it becomes unnecessary. A deeper framework may explain why apparent multiplicity emerges from something more basic. Or it may confirm that multiplicity is fundamental. What matters is not the outcome. What matters is the method. Physics will not decide the multiverse by preference or philosophy. It will decide it by consistency, coherence, and constraint. This process is slow, measured in decades, not headlines, But that slowness is a strength. It prevents premature certainty. The multiverse is not the end of physics. It is a sign that physics has reached a scale where our intuitions no longer guide us. And that has happened before. Every time understanding expanded. Living with an open multiverse, the most important thing about the multiverse is not whether it is true. It is how it changes our relationship to certainty. For centuries, people hoped physics would deliver closure, a final theory, a complete description, a reason everything is the way it is. The multiverse disrupts that expectation. It suggests that reality may not funnel toward a single outcome, that laws may permit many realizations, that explanation may stop before preference begins. This does not weaken science. It clarifies it. Science explains how structures behave. It does not guarantee that structure itself must be unique. Living with an open multiverse means accepting that knowledge has horizons, not temporary ones, structural ones. This does not mean anything goes. Constraints remain strong. Physical law remains precise. Prediction remains powerful locally. What changes is our attitude. We stop demanding that the universe justify itself completely. We stop mistaking discomfort for incoherence. An open multiverse does not remove meaning. It removes cosmic entitlement. We are not owed uniqueness. We are not owed centrality. We are not owed final answers. What we are given is structure, time, causality, possibility. Within that structure, life can happen, understanding can happen, care can happen. The multiverse does not tell us what ultimately matters. It tells us that what matters is not decided globally. It is decided locally by beings who experience consequences. And that may be the most realistic foundation for meaning that physics allows, not infinite validation, not cosmic preference, but situated significance. If the multiverse is real, then this universe is one expression of a broader reality. If it is not, then this universe is still vast enough to dwarf certainty. Either way, nothing important changes about how you live tomorrow. Responsibility remains. Care remains. Choice remains. Physics does not tell you how to live, but it tells you what kind of universe you are living in. And that universe, whether singular or multiple, does not close. It remains open, unfinished, still unfolding. And so does understanding. Is the multiverse inevitable? Following the mathematics honestly, a crucial question remains unanswered. Not whether the multiverse is strange, not whether it is comforting, but whether it is avoidable. Physicists are trained to be conservative. They do not add entities lightly. They prefer fewer assumptions, not more. So when the multiverse appears again and again in otherwise successful theories, the reaction is not excitement, it is suspicion. The key issue is this. When we write down the equations that best describe reality so far, do they force multiplicity? Or are we smuggling it in through interpretation? In quantum mechanics, the fundamental equation, the Schrödinger equation, is linear and deterministic. It never selects a single outcome. It evolves superpositions smoothly over time. Nothing in the equation says only one result may exist. To recover a single, observed outcome, we must add something. A collapse rule, a hidden mechanism, a modification of the equation. Each of these additions has consequences. Collapse theories introduce randomness that violates conservation laws or must be tuned extremely carefully. Hidden variable theories introduce non-locality that sits uneasily with relativity. Modified dynamics risk contradicting experiments that already confirm quantum mechanics to extraordinary precision. The many worlds interpretation does none of this. It changes nothing in the equations, it simply takes them literally. That is why many physicists say the multiverse is not an interpretation of quantum mechanics. It is what remains when you refuse to add untested assumptions. Cosmology tells a similar story. Inflation was not proposed to generate other universes. It was proposed to explain the structure of this one. But once inflation is allowed, eternal inflation emerges naturally in large classes of models. To stop it, one must carefully tune parameters or impose special initial conditions. Again, extra assumptions. String theory deepens this tension. It does not produce a single vacuum solution. It produces a vast space of consistent solutions. No known principle selects one uniquely. Physicists have searched for such a principle. None has been found. So the question becomes unavoidable. If the theory allows many consistent universes, on what basis do we insist only one exists? At this point, resistance to the multiverse often becomes philosophical rather than physical, which is not a flaw, but it must be acknowledged honestly. The multiverse may still be wrong. Future theories may eliminate it, but as of now, it is not something physicists add. It is something they struggle to remove. This is the strongest argument for the multiverse. Not that it explains everything, but that it may be the simplest outcome of theories that already work. And physics has learned, repeatedly, that nature does not adjust itself to preserve human expectations of simplicity. What the multiverse ultimately changes, and what it leaves untouched if the multiverse exists, what truly changes, not emotionally, not philosophically, but physically, surprisingly little. The laws you experience tomorrow do not change. Gravity will behave the same way. Atoms will bond the same way. Time will move forward the same way. No experiment in your kitchen, no choice in your life, depends on whether other universes exist. This is an important point. The multiverse does not interfere with local causality. It does not alter dynamics. It does not rewrite everyday physics. What it changes is how explanations terminate. In a single universe picture, we expect every fact to trace back to necessity. Why this constant? Why this symmetry? Why this beginning? In a multiverse picture, some facts stop earlier. They become environmental, like asking why Earth is rocky instead of gaseous. The answer is not fundamental, it is contextual. This reframes curiosity, but it does not suppress it. We still ask, why this framework? Why this mathematical structure? Why these rules at the deepest level? The multiverse does not close inquiry. It relocates it. What it does not change is experience. You still live one life. You still make decisions with irreversible consequences. You still exist in one branch with one future. The multiverse does not allow escape. It does not soften loss. It does not dilute responsibility. If anything, it removes the last illusion that something else will balance things out. Nothing balances things out. Only what happens here matters here. The multiverse also does not diminish wonder. It expands it, not by adding fantasy, but by extending humility. Reality may be larger than any single narrative, larger than any single universe, but understanding remains local. And locality is where all experience lives. Whether the multiverse is real or not, this conclusion survives. Physics does not promise that. Reality will revolve around us. It promises coherence, consistency, and constraint. And within those constraints, life is allowed to exist, to care, to ask questions. The multiverse does not answer why anything exists. It clarifies how much explanation physics can offer without overreaching. And that clarity, not certainty, is the true achievement of science at the largest scales. The multiverse is not many copies. It is many conditions. One of the most persistent misunderstandings about the multiverse is the idea that it consists of many copies of the same universe. This picture is simple. It is also mostly wrong. In real theoretical physics, the multiverse is not primarily about repetition. It is about variation. Different multiverse models emphasize different kinds of diversity, but they share a common theme. What changes from universe to universe is not just history, it is conditions. In inflationary multiverse models, each universe may emerge from a different vacuum state. That vacuum determines the strength of forces, the masses of particles, the stability of atoms, the behavior of space-time itself. These are not small differences. They are structural. Some universes would expand too fast for matter to clump. Some would collapse immediately. Some would form only black holes. Some would never allow chemistry. Most universes in these models are sterile. They do not fail dramatically. They simply never become interesting. This is why the multiverse is not a story about infinite civilizations. It is a story about overwhelming emptiness. The many worlds multiverse is different, but the lesson is similar. Here, the laws do not change. The initial conditions do. Different measurement outcomes lead to different macroscopic histories. Again, most branches are unremarkable. They differ only in microscopic detail. Only a tiny fraction lead to radically different futures. This matters because it clarifies what the multiverse is not. It is not a collection of fully realized alternative, lives a cosmic replay of every fantasy, a guarantee that everything happens. Physics does not permit arbitrary worlds. It permits lawful variation. Every universe in any serious multiverse model is constrained by mathematical consistency, physical law, dynamical stability. There is no universe where contradictions occur. There is no universe where anything goes. This is why physicists talk about a landscape, not chaos, a structured space of possibilities, most of which are uninhabitable. From this perspective, our universe is not typical, but it is also not miraculous. It sits in a narrow band where long-term complexity is possible. The multiverse does not explain why this band exists. It explains why we find ourselves within it. This is a subtle but crucial point. The multiverse is not an answer to why this universe. It is an answer to why this kind of universe is observed at all. And once framed correctly, the multiverse stops feeling extravagant. It starts to look like what happens when physical law is allowed to explore its own consequences. The multiverse and the end of cosmic privilege throughout the history of science. One pattern repeats. We discover that we are not central. Earth was not the center of the solar system. The sun was not the center of the galaxy. The galaxy was not the center of the universe. Each discovery felt destabilizing. Each turned out to be clarifying. The multiverse continues this sequence. It removes the last remaining form of cosmic privilege. In a multiverse, there is no central universe, no preferred timeline, no unique realization of physical law. This does not mean that our universe is unimportant. It means that importance is not assigned by position in reality. Physics has taught us this lesson repeatedly. Being typical does not determine value. Being central does not determine meaning. From a physical standpoint, our universe is one realization of a deeper structure. From an experiential standpoint, it is everything we will ever encounter. Both statements are true. The multiverse forces us to hold these truths simultaneously. And that is uncomfortable, because humans evolved to think in terms of uniqueness. But physics does not reward intuition, it rewards consistency. The multiverse also removes a subtle but powerful assumption that reality must be arranged in a way that makes us special. In a multiverse, life is not guaranteed. Meaning is not guaranteed. Observers are not guaranteed. When they appear, they do so without cosmic ceremony. They arise because conditions allow it. And when conditions no longer allow it, they disappear. This does not cheapen existence. It grounds it in a universe that is not centered on us. Responsibility cannot be deferred upward. There is no cosmic narrative that will redeem outcomes automatically. What happens here is not balanced elsewhere. There is no larger story in which loss is cancelled. The multiverse, paradoxically, makes local reality more serious, not less. If nothing guarantees meaning, then meaning must be practiced. If nothing guarantees justice, then justice must be enacted. If nothing guarantees continuity, then continuity must be protected. The multiverse does not absolve us. It removes excuses. and that may be its deepest, quietest consequence. Not a change in equations, not a change in prediction, but a change in how honestly we locate ourselves in reality. We are not the center, we are not the goal, we are not the explanation. We are a consequence, a lawful one, a rare one, a temporary one, and in a multiverse vast enough to allow countless outcomes, this one still happens. This universe still exists. This moment still unfolds. That is not diminished by what exists elsewhere. It is defined by what happens here. The multiverse and the question physics may never settle. There is a question that sits quietly beneath every discussion of the multiverse. Not whether it is beautiful, not whether it is unsettling, but whether physics will ever be able to decide. Physics is powerful, but it is not omnipotent. It operates under constraints that are not technical, but structural. Light travels at a finite speed. Information is limited by causality. Observers are embedded inside the systems they study. The multiverse pushes all of these limits at once. Other universes, if they exist, are causally disconnected. No signal can cross the boundary. No experiment can directly sample them. This creates a genuine scientific tension. On one hand, physics demands empirical grounding. On the other, some of our best theories seem to imply structures that lie forever beyond observation. This does not automatically disqualify the multiverse, but it does force physics to confront its own scope. Historically, physics has expanded by allowing indirect inference. We inferred atoms before we saw them. We inferred black holes before we imaged them. We inferred neutrinos before we detected them. In each case, the entities left fingerprints. They altered predictions. They shaped outcomes. They constrained alternatives. The multiverse may or may not do the same. That remains an open question. What makes the multiverse different is not invisibility. It is inaccessibility. Other universes are not merely hard to detect. They may be fundamentally unreachable. This raises a profound issue. If a theory is mathematically consistent, empirically successful in all observable regimes, predictively powerful locally, but implies unobservable consequences, do we accept those consequences or reject the theory? There is no algorithmic answer. This is not a failure of physics. It is an encounter with its limits. Some physicists believe future theories will eliminate the multiverse by introducing new principles that enforce uniqueness. Others believe that multiplicity is a genuine feature of reality and that physics must adapt to that fact. At present, both positions are intellectually respectable. Neither is proven. Neither is ruled out. This is an uncomfortable place to be, but it is also a familiar one. Physics has often advanced by sitting with unresolved tension for long periods of time. The multiverse may be decided, or it may remain an open consequence of deeper theories without independent confirmation. Either way, physics will not collapse into speculation. It will continue to map what can be known, what can be constrained, and where explanation legitimately stops. If the multiverse remains undecidable, that will not mean physics failed. It will mean physics discovered a boundary it cannot cross, and knowing where boundaries lie is itself a form of understanding. What the multiverse leaves us with, after everything physics can say about the multiverse, something important remains unchanged. You still live in one universe, one branch, one history, one unfolding sequence of moments. The multiverse does not give you access to alternatives. It does not allow revision. It does not soften consequences. From the inside, reality behaves exactly as it always has. Causality holds. Time flows forward. Choices propagate. This is not an accident. Physics does not allow cross-branch interaction. Each universe, each branch, is dynamically isolated. That isolation is what makes experience coherent. Without it, there would be no stable observers, no memory, no identity, no responsibility. So even if the multiverse exists, Nothing about lived reality becomes vague. If anything, it becomes sharper. You cannot appeal to other outcomes. You cannot rely on cosmic redundancy. What happens here happens fully. The multiverse does not undermine meaning. It explains why meaning is local, why it depends on memory, connection, and consequence. Physics does not assign value, but it tells us something crucial. Value does not need to be universal to be real. In a multiverse, no single universe carries cosmic authority, but every universe carries its own internal seriousness. This reframes humility. We are not special because we are chosen. We are special because we exist at all, under narrow conditions, for a limited time. The multiverse does not turn existence into noise. It reveals how selective existence already is. If reality allows countless possibilities, and only a few allow awareness, then awareness is not trivial. It is constrained, rare, fragile. The multiverse does not explain why reality exists. It does not close the deepest questions. What it does is remove the expectation that the universe must revolve around explanation. Physics reaches a point where it can say, "This is how far structure carries us." Beyond that, there is no failure, only restraint. And restraint is one of the quiet strengths of science. It refuses to speak where evidence does not reach. Whether the multiverse is real or not, this much remains true. Reality is larger than intuition. Understanding is local. Experience is finite. Responsibility is unavoidable. And within one universe, this one, that is enough to live honestly. Living in a universe that may not be alone at this point in the story, we have followed physics as far as it can responsibly take us. We've seen how quantum mechanics refuses to select a single outcome. We've seen how cosmic inflation may never fully stop. We've seen how modern theory repeatedly allows, and sometimes demands, more reality than we can ever observe. This is where the multiverse enters, not as a claim, not as a belief, but as a consequence. The multiverse is not an additional layer added for wonder. It is what remains when physicists do not interfere with equations that already work. When quantum theory is taken literally, all outcomes persist. When inflation is allowed to run according to its mathematics, many regions form. When fundamental laws allow multiple consistent solutions, nothing selects only one. The multiverse appears not because physics wants it, but because physics cannot easily avoid it. And yet, something crucial must be said clearly. The multiverse is not something you experience. You do not move between universes. You do not communicate across branches. You do not live many lives. From the inside, reality remains singular. One history, one arrow of time, one chain of consequences. Physics protects this locality. Without isolation, memory would fail. Identity would fail. Experience itself would collapse. So even if the multiverse exists, your life is not diluted. Nothing you feel is averaged across realities. Nothing you do is cancelled elsewhere. Meaning does not leak. Responsibility does not disperse. What does change is how explanation ends. In a single universe picture, we expect everything to be necessary. In a multiverse picture, some things are conditional. Why these constants? Why this vacuum? Why this beginning? The honest answer may be, because this is where observers can exist. Not because life was intended, but because observation is selective. This is not circular reasoning. It is constraint. Fish observe water because without water, fish cannot exist. Observers observe compatible universes because incompatible ones are unobservable. The multiverse does not explain why the laws exist, why mathematics works, why there is something rather than nothings, has never claimed to answer these questions. The multiverse does not pretend to. What it does offer is clarity. It tells us where explanation legitimately stops. It tells us that uniqueness is not guaranteed. It tells us that reality may be larger than observation allows, and then physics does something important. It steps back. At this boundary, science does not collapse into speculation. It becomes disciplined. It says, here is what our best theories imply. Here is what we can test. Here is what remains open. That restraint is not weakness. It is integrity. So where does that leave us? Right where we have always been, living in one universe, making irreversible choices. Experiencing time one moment at a time. Whether or not other universes exist does not soften loss, does not excuse harm, does not guarantee meaning. If anything, the multiverse removes the last illusion that meaning is handed down from the structure of reality itself. Meaning is local. It arises where experience exists, where memory exists, where consequence exists. Physics does not tell us what matters, but it tells us something equally important. Nothing else will decide for us. The universe, singular or multiple, is lawful, indifferent, and vast. And within it, for a brief window, there are beings capable of understanding part of it. That understanding does not need completion to be real. The multiverse may be true. It may be replaced. It may remain undecidable. But one thing is certain, this universe is real enough to live in fully, and that is where physics always leaves us. Not with certainty, not with closure, but with orientation, a clear sense of where we stand inside something much larger, and a reminder that what happens here still happens completely.